Okay, so welcome back. So we are still in section 6 of chapter 2, and we are still discussing some techniques so that we can manipulate our differential equation such that it is either separable, exact, or linear. Because we know how to solve separable, exact, or linear. We are just or I'm just giving you some resources that you can use to manipulate equations into one of those forms. Okay? So here is another technique. So let's just imagine, my apologies. Let's just imagine that you have solved, or you have your differential equation solved for dy dx. If you don't mind, let me just show you an example. So notice how this differential equation is solved for dy dx. So now, what we want to do, as long as the right side of the equation can be expressed in terms of ax plus by. Right, I'll give you an example. So let's say you have dy dx is equal to, my apologies, dy dx is equal to, and I'm just going to make something up. Let's say x, my apologies, let me not write with a stylus. And I'll just do it this way. Example. Dy dx is equal to, and let me now make up something. X plus y plus 2 plus x plus y squared. So notice that ax plus b times y, the a and the b, these are just constants. So now I have x plus y here, I have x plus y here. So if that's the case, if I defined x plus y to be z, I could literally take this right-hand side of the equation, and wherever I see an x plus y, I could insert a z. Right? So do you see how I could write that as z plus 2 plus z squared? So that's the idea informally. That's the idea of what we're trying to do. Just, does it make sense that if this was x plus y and this were x plus 2y, that wouldn't work, right? Because I need to be able to plug this z in for the entirety of it. It needs to be expressed entirely in terms of the same ax plus by, so that I could substitute that z. Okay. So again, we're going to learn by example as opposed to really diving into the theory. So let's just assume that you can express the right side as ax plus by. If you can do that, right, just like I have over here, then what we're going to do, this is the procedure, and we'll see it come alive with an example. We are going to define that ax plus by as z, so that I'm going to plug a z in here. Then we're going to differentiate we're going to differentiate with respect dz with respect to we're going to differentiate z with respect to x, is what I'm attempting to say. And that's what we're going to solve in for. We're going to sub in for dy dx. I'll tell you what, if you don't mind, because at some point, you guys are going to kill me if I go in too deep. Let me give you the how about a, in other words, quick method, right? So step 1 is to substitute a z, and step 2 is to substitute 1 minus dz over dx. Okay, so let me just explain. This is if I were talking to my son, Sebastian, he's only 11 years old, I'd say, hey, Sebastian, what you're going to do is you're going to just put a z here, put a z here, anywhere where you could have an x plus y. And then, hey, Sebastian, then you're just going to take this 1 minus dz over dx, and you're just going to put it here for dy over dx. You're going to do that every time, okay? And that way I don't have to elaborate, but seriously, if you just take the derivative of this with respect to x and then solve for dy dx, this is what you would get. So let me now go ahead. This is our procedure. Let's grab that. Let's go to the example on the next page. Okay, so we'll park that here. All right, ready? So here we go. So we have this equation's already solved for dy dx. Now the real question is, can we manipulate the right side of this equation so that you can have it expressed in terms of z is equal to ax plus by. Okay, I need to be able to. In other words, I need to be able to sub in a z everywhere over here where there's, with these, instead of having these x's and y's. So how could we possibly do that? Well, let me just go ahead and write the thing that we're working with. Okay. So what we're going to do is we're going to group. We're going to try to group some stuff here. So I'm going to group here. I'm going to group here. All right. Well, notice that these don't match right now, right? I mean, the y is positive here, but the y is negative here. The x is negative here, but the x is positive here. So, okay, so I can't put a z in here yet, right? Because it has to match. But watch what happens if I just factor out a negative 1 here. Then I would be left with a negative y and a positive x, which is exactly what I have over here, a negative y and a positive x, okay? So that's what I'm going to do. I'm just going to factor out a negative 1. And now that would be, I'm just going to write it as x minus y with me. I mean, so that it looks, this x minus y looks like this x minus y. But you see what I'm doing. If you factor out a negative 1, all I did was, of course, the x turns positive, the y turns negative. I just rearrange them so it looks like this. Still have minus 1 plus, and again we have x minus y plus 2 raised to the power of negative 1. All right, so that is exactly what we needed. Let's see if I can give myself a little bit of space here. So that is exactly what I needed so that I can use that substitution. Are you ready? So remember, that was equal to dy dx. This is equal to dy dx. Okay, so what's going to happen right now is anywhere I have an x minus y, I'm going to insert a z. And then I'm going to just take the left side of that equation and insert 1 minus dz dx. Okay, so 1 minus dz dx is equal to negative 1, so that's just simply going to be negative z minus 1 plus, alrighty, z plus 2 to the power of negative 1. Okay, so I would always suggest that, because, you know, if you use substitution, eventually you got to back substitute. So go ahead and write yourself the note that z, you have defined z to be y minus x. That's what you did for this problem, okay? All right, well, guess what? So now we are, now we have a differential equation that is separable. So let's go ahead and clean this up a little bit. So I'm going to take this one, bring it to this side of the equation. Let's see what happens here. Yeah, so yeah, let's bring this one over here, and then I'll probably just get rid of this negative symbol. So let me just do that right now. So I'll do that in 2 steps. Negative dz dx is going to be equal to negative z. So if I subtract 1 here, subtract 1 here, that would be minus 2 plus z plus 2 to the power of negative 1. Okay, and what I'm going to do right now is just get rid of this negative symbol. Just, you know, divide by negative 1, divide by negative 1, divide by negative 1, divide by negative 1. All right, and that'll finally get me to dz dx is equal to z plus 2 minus z plus 2 to the negative 1. Okay. So at this stage, this is separable. What you would do, remember, if it's separable, you want your dz on one side, your dx on the other side. To do this, I'll show you really quickly. It's just, you would multiply by dx on both sides. Okay, that would get rid of this dx here. And notice, look at the right side of that equation. Notice how everything is in terms of z. So we're literally going to take all of this and move it to the other side of the equation. Okay? So that all we have is z plus, how do I want to put this? Yeah, so z plus 2 minus z plus 2 to the negative 1. Trying to finish this with the space that I have. All I would have over here is dx. Okay, so this would all be over 1 dz. Okay, so all I'm trying to do is clean this up so it looks a little bit better. So distribute, this is dz. Okay, so again, what just happened? What the heck just happened? Well, distribute a dx, right? So if once you distribute the dx, these dx's cancel, and you're left with just dz. But now you want to get, but now if you think about having dx over here, now, you would divide by all of this. Okay, all of this that's attached to dx, so that you're here. All right, now, at this stage, obviously we integrate both sides. I would not be very happy about integrating this the way it sits. So what I'm going to do is take this to the next page. Go ahead and grab another page here. Let's go ahead and clean this up a little bit. Okay, because if I'm going to integrate both sides of this, I don't want to integrate this the way it sits. Let's make sure, let's move these things around. So obviously, if you anything to the power of -1, I can move that to the numerator, so that all that I have at that point is, what do you got? I got z, well, here's what I have after moving some things around. I have z plus 2 over z plus 2 squared minus 1 dz is equal to dx. If you, let me do this. I have no idea. Yeah. Listen, if you want the steps of how I was able to manipulate this to here, just reach out to me. But, you know, it can be during office hours, or you can email me. That's, either one is fine. I mean, it's a bunch of little algebra and you know, fractions, common denominators, all that stuff. But this is just a lot nicer to integrate. So z plus 2 over z plus 2 squared minus 1. All right, we integrate. This is just a lot easier to integrate. I would use u substitution here. For this side, I would literally let u equal z plus 2 squared minus 1, then take du. When all is said and done, so let's start with the right side. The right side's easy. So if you integrate, this is literally like integrating 1, right? So that's just x plus c. And now if you integrate the left side using that u substitution, you end up with 1/2 ln of z plus 2 squared minus 1. Again, the goal is going to be able to get z by itself. So let's go ahead and get rid of the half. We can get rid of the half if I just multiply by 2. All right, at this stage, again, the goal is to get z by itself, so let's exponentiate both sides. That just leaves me with z plus 2 squared minus 1 is equal to, and just like I've said many times, we're going to write this as e to the 2x, e to the 2c, and all of this is going to turn into just c. So we're going to write that as e to the 2x times e to the 2c, and this is just e to the 2c is just one big constant for our purposes. All right, so z plus 2 squared minus 1 is equal to c e to the 2x. Okay. So at this stage, remember we do need to solve, we either need to solve for z, or we can leave it in implicit form, okay? That we can leave our solution in implicit form if we have to. But at some point in time, we have to go back in, right? Remember, we defined z to be y minus x, so we have to go back in and plug in a y minus x for z at some point in time. So I'm going to do the best I can right now. I'm going to go ahead and plug this y minus x back in here for z, and at the same time I'm going to just bring this -1 to the other side of the equation. So what does that look like? X minus y plus 2 squared is equal to c times e to the power of 2x plus 1. This is about as good as we're going to get this one, okay? At this stage, it would be nice to solve for y, but that's not going to happen. That's not going to happen right now. So we're going to leave our solution in implicit form, all right? We're not going to be able to explicitly define it for y. Okay, that's another technique for your belt there. I'll see you in the next video.